Awful quiet this morning. Good morning, how we doing? Waking up? Get to that point halfway through the semester where you're just like, will it ever end? Right? You're just on that hamster wheel, running and running and running. I know. Keep at it. Remember, it's a marathon, not a sprint. These are the 4 toolboxes we've covered so far. And what we're going to do for the next 2 chapters is do these all over again. Only we're going to do it in circles. My goal today is to convince you, or at least try to help you understand, that what we're doing isn't all that new. It's like 10% new, but 90% what we've done before. Today, we're going to do kinematics. We're going to cover kinematics. I might even get started into Newton's laws. We'll see. But we're going to tackle kinematics specifically for things in rotation. We've done rotation before. We've done centripetal acceleration and circular motion. Those were kind of a little bit warm-ups to what we'll be doing today. But even though, honestly, the symbols are going to look different, the ideas behind those symbols are the same. And we've been here before. We've done kinematics before. And so we're going to borrow from a lot of what we already did before. And don't panic if you don't remember it. Does chapter 2 and chapter 3 feel like light years ago? Right? After Newton's laws, it's like, did I even live before Newton's laws, right? So don't worry. We're going to help you through, right? We're going to give you one more toolbox for Physics 2A, and that will be in chapter 10. It's called Simple Harmonic Motion, which is sort of a combination of all of these things put together in a different way. And those will be the 5 toolboxes that will carry us through the end of the semester, and then on to Physics 2B. You'll be using these toolboxes over and over again. So we've been heavy on giving you these toolboxes, and after chapter 9 and 10, it really gets heavy into like application and just applying these toolboxes over and over and over again. So good news, plenty of practice for us to, if we're a little bit loosey-goosey on like, oh, Newton's laws, free body diagrams, don't make me do it again. Well, I'll make you do it again, but like the second time through, tend to get a little bit more of a hook for your brain. So we need to talk rotation. We really need to talk about how we're going to talk about things going in circles. That was redundant. And I want to start with my bicycle tire here. Now, this is not a typical bicycle tire. This bicycle tire, hold that for me just real quick with both hands. Is it pretty heavy? Yeah, a little bit. Okay, right? This tire actually has metal. It's got iron metal inside the rubber of this tire. We're doing that on purpose to make something called the moment of inertia very big. We'll get into that later. But I just wanted you to know that, yes, I do have physics muscles, but when it looks like I'm getting tired up here holding this thing, it's actually not. It's heavier than a regular bicycle tire. Okay, so let's say that we were an ant or something, right? On the edge of this bicycle tire, right here where I put this mark, right? And if I set the bicycle tire in motion, okay, it can be a little bit difficult, or at least harder than it needs to be if we were to talk about the, say, position of this ant in terms of X and Y. I mean, we could do it, right, okay? But there is a more natural system in which we can talk about where this ant might be located at any time. Does anybody know what I'm talking about? Up till now, we've done Cartesian coordinates. So now what are we going to do?
I forgot the name of it, but the second system of coordinates that do distance from center and angle.
Radius and angle, otherwise known as polar coordinates?
Polar.
Yeah, okay, then now everybody just clocked out and wants to die, right? Because you might remember the trauma associated with trying to learn polar coordinates, say in high school or something like that, right? Okay. Don't worry. It actually turns out to be a really natural system for talking about where this ant is. Is this ant ever changing its distance from the center of the tire? No, right? So that's going to stay constant. And what we're going to do is we're going to measure with an angle, right, where this ant happens to be at any particular time. Circles also do some kind of weird things, like if I wanted to talk about the displacement of this ant, right? If I start it here and I send it all the way around, where'd it go? Went too far, right there, okay? If I send it all the way around once, well, what's its displacement? It's 0, right? It's like, well, it didn't go anywhere. Well, it traveled a distance. The distance happens to be the circumference of the wheel, right? Okay, but so there's a few little niggly bits in here. So let's start at the very beginning with a language, okay, for how we can talk about things moving in circles. And so we have sort of the standard unit circle, whatever it is you want to call it, right? And if I have something that's like right there on my circle, then we can measure how far it is from the center of the circle, and we can measure the angle that it's at. And a change in position is going to be a change in angle, really. But how do I talk about? Okay, so we can talk about the actual distance that this ant traveled from, and again, just to be clear, right? This is 0 degrees up high to the top is. This is your time to shine. 90, 180, 270. So standard. Cartesian, angles and all that sort of stuff. All right, and we've been doing a lot of this already. We've done trig and vectors, and so we're familiar with this. But if I want to talk about that distance there in orange, does anybody remember what that's called? Ooh, arc length. Okay, the arc length. And the arc length has units of meters. So S here being sort of a generic way to talk about the distance something travels, okay? It's not an X or a Y, it's just some distance S, okay? The units of S are meters. Well, what are the units of R? What is R? Like, is it a distance? Is it a time? What is it? It's a distance, right? And what unit do we measure distances in? Meters. Okay. Well, so far I've got a meter equals a meter, right? Okay. So what units does theta have to have in order for meters to be equal to meters? So we got to multiply by a theta here, right? What are the units of theta? It has no units. Because I got to multiply by something that has no, not 0, right? But in terms of units, I've already got a meter. I got a meter equals a meter, and I want to multiply by something else. It better have no units attached to it. Otherwise, I'm going to mess up what's going on here. Now, many of you said degrees. What's a degree? It's 1/360th of a certain. I don't. 360. Seriously? Like, who came up with that number? And can we go back in time and fix it?
Might have been the Mayans, I'm not sure.
It wasn't Maya, it was the Babylonians.
Oh.
Yeah, when it comes to time and degrees, just blame the Babylonians. They in their culture, powers of 6 and 60s and things like that were very significant. They did base 60 mathematics. You think you guys have it bad? No. Try being a high schooler in ancient Babylonian. That was bad. Okay? But, so it gets real uncomfortable not having a unit to attach to something. And the unit is not degrees. Does anybody else know what the other unit is?
Radians?
It's radians. Okay? So what are the units of radians?
180 degrees would equal to 2 pi.
It's a unitless unit. I'm sorry. There's no other way for me to talk about this or teach it. And it's something that your math teachers decided to never tell you. A radian is a label. It's something we attach to a measurement of an angle so that we just aren't left hanging there, right? We don't just go 2.4 or 3.14159. So, okay, so I just laid out pi, right? What is pi? What's pi? Okay, that's the approximation, right? 3.14159 blah, blah, right? Okay. But what is it? Besides peach and apple and cherry and all the good times. Does anybody remember the definition of pi? It's the ratio. It's okay if you don't remember. I don't remember high school either. Of the circumference of a circle to its diameter. How do we measure the circumference of a circle? Like what unit do we use? Again, is it a velocity, time, length? What is it? It's a distance, it's a length, right? And what about the diameter of a circle? What is it? It's also a length. And so if you take a length and you divide by a length, what do you get? You get no units, right? And yet, a mathematician will go, well, this is 3.14159, blah, 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 radians. I'm not don't look at me like that, okay? I'm not responsible for that. I guess I'm responsible for perpetuating it. But it is what it is, okay? And then on the circle, like, don't we have ways of talking about how many pies? So like if you go around halfway around the circle, how many pies is that? It's 1 pi going halfway. But to go all the way around is how many pi? It's 2 pi, isn't it, right? Pi over 2 at the top, 3 pi over 2 at the bottom, right? That kind of stuff. That's all hiding in there, right? But we can kind of get back and forth to something that is in meters, and then a position that's given as a radius times a angle. We can get back and forth between that. So we can talk about where the ant is, right, on this wheel by saying, well, we know the distance from the center, and then we have some angle, right? Okay, if it's 180 degrees, we know he's over there. If it's pi over 2, we know it's over here, right? How do we talk about how fast the ant is going around on this wheel? Because there's a difference between the speed that the ant is moving here and the speed that the ant is moving here, right? What's the thing that's changing in time? Is it r or is it theta? It's theta, isn't it? Okay, so it's the angle that changes. So if I want to, so back in the day, right, when we were talking about velocity, right, we said it was a change in distance, a change in position, a change in x or y or whatever, right, in time. What we have now is a change in like arc length, right? And so we know it's not the radius that's changing, it's the theta. And so if I go and I divide this by time, I'm now getting an idea here, right? A change in angle, right, over a change in time. And we're going to go ahead and we're going to define this. We're going to say that delta theta over delta t, we're going to call that the angular velocity. going around like this, it has one angular velocity. If I speed that up, right, it's got a different angular velocity, okay? Can we have negative angular velocity? If it's going the other way? Sure, right, okay? So you can have two different ways to talk about it. But the thing that's changing is the angle here, right? Not the distance from the center. What symbol are we going to use for that? One of the things you may or may not have noticed yet is that we seem to be going Greek. As soon as we get into rotation, we're using thetas, right, instead of x's and y's and linear things, okay? So we're going to keep the theme up, and we're going to use this symbol right here. Now, fair warning, okay? You need to understand that that letter is the Greek letter omega, the lowercase Greek letter omega. That is not, and I hesitate to plant this association in your brain, but you're probably already there anyway. That is not a W. This is a W. That is an omega. What's the difference? Focus. Right? Okay? I tend to get irrationally upset if you call this a W. Right? So just, again, I'm warning. I used to throw chalk. I don't throw things anymore. All right. So that right there, omega, is our angular velocity. You're going to learn Greek today, by the way, in addition. Okay, so the other thing that we did back in the day, right, is that we took this change in velocity in time, and what did we call that? That's acceleration, right? It's a change in motion. We gave it the symbol A, and away we went. And I still don't understand what it means, Mr. Bailiff. Well, yeah, sometimes on a bad day, neither do I. So if I change omega in time, what does that look like? So if I have this wheel that's just moving along, right, okay, doing its thing, and I speed it up, did its omega change? Yeah, right? The omega changed. It sped up, right? And so that means I had some kind of acceleration going on, and it just happened to be an angular acceleration. I wonder if there's a Greek letter that's a lot like an A, but in Greek. Alpha! Alpha looks like a little fishy, right? And so we're going to use alpha as our symbol for angular acceleration. And again, an acceleration is a change in motion, is it not? So an angular acceleration is a change in rotation. So if the wheel isn't spinning, and then I give it a push, I caused an alpha to happen, right? It accelerated. Right now it's not accelerating because it's just moving at constant speed. I can give it a bigger push and speed it up, right? And then I can apply some friction to this to cause an acceleration. That would be a deceleration or negative acceleration, okay? But it all ties directly back to the things we did in straight lines. Just now everything's moving in a circle. So these are more definitions, right, to hang our hat on in terms of how we're going to move into the next part, which is the kinematic equations. Oh, yeah, okay, I need to show you this. I'm going to show you this now, not use it very much, but it's going to come back to haunt you in Physics 2B. So this isn't oh, you better remember this or you're going to die. You're probably not going to remember this at all. But what we need is your brain to have seen it now, so that next semester when we're teaching it to you again, your brain kind of goes, oh wait, oh yeah, there was something like that. And it'll be a little bit more prepared for it. Here's the problem, okay? If I'm spinning this wheel, what direction is this wheel spinning? Ooh, counterclockwise. clockwise. What's a clock? Nobody uses clocks anymore, right? Okay, well that's a watch, right? Okay, but yeah, so the clockwise and counterclockwise, right? So this wheel is spinning counterclockwise right now? Yeah? Everybody agree about that? Well, I don't. Because from my point of view, which way is the wheel spinning? Clockwise. You see the problem? Okay? Now, that being said, we will often use clockwise and counterclockwise to talk about the direction of rotation or something. Because we'll draw a picture on the page and everybody's looking at the page from the same direction, right? But in practice, in reality, it can be very difficult, depending on the point of view, to decide which way the wheel is spinning. Which is why we have something called a right-hand rule that helps us always determine which way it's spinning, regardless of the point of view. Let me demonstrate for you, okay? What you do, I'm going to demonstrate this way, okay? I'm going to demonstrate this way. So what you do, okay, is you do something, I call it hitchhiker, okay? When you don't hitchhike, right, okay? But if you were to, right, you curl your fingers into your palm and stick your thumb out, right, okay? What you want to do is you want to take your hand, do it right now, everybody raise your right hand. Repeat after me or something. Just want to make sure everybody knows which one is their right hand. Good, okay, you can put your right hands down. It's one of the preeminent philosophers of our age, okay, said this. And the philosopher's name is Winnie the Pooh. He said, I have no trouble telling my left paw from my right. It's knowing which one to start with that makes all the difference. That's deep. That's really deep. Anyway, okay, so, and I was only half joking about being the preeminent philosopher of our age. You hold Winnie the Pooh up against Congress and Winnie the Pooh wins every time. Okay, so, if I spin it like this, take your right hand, take your fingers, and wrap them around in the direction the wheel is spinning. See how I'm wrapping them around this way? Okay? And which way is my thumb now pointing? Directly at you guys, right? Okay? Notice, if I do it from the back side, where I would say it's going clockwise and you say it's going counterclockwise, if I do it from the back side, I still wrap my fingers around the direction the wheel is going, and which way does my thumb point? Same direction you guys would have it pointing. And we can do it this way too, right? Okay, if I reverse everything, now which way is the wheel spinning? Fingers wrap around like this, and thumb points towards the board, doesn't it? But this gets even better. And don't panic, you won't make you do this, okay? But what happens if I hold the wheel like this? Now, how do we agree on clockwise or counterclockwise? You really can't, can you? But what you can do is say, oh, well, I know it's spinning around. Wrap my fingers around the direction it's spinning. And which way is my thumb pointing? Up, right? So this can account for any orientation of a spinning object in 3D space. And always be agreed upon as long as everybody's using their right hand. Sorry, left-handers. Okay? Yeah, I know. You always get the short end of the stick, don't you? So that, if you hear about a right-hand rule, you're watching a video on YouTube and they're saying right-hand rule this, right-hand rule that, this is what they're talking about, right? They're establishing a direction for the angular velocity. Okay, so make sure I get the symbology right. Let's see. Let's go back to some old friends. We had equations, I think, that looked a little bit like this, didn't they? T plus 1/2 AT squared. V squared equals V naught squared plus 2A. Remember those? Back in the days when you thought physics was hard. These are the linear versions, right? For things that are moving in straight lines. Cars accelerating along a road. Dropping an object. We can even make it a little bit more complicated, throw something in the air, and with our power of vectors, split the x and the y directions into separate, one-dimensional, linear things. Well, now we're going to do it in rotation. I'll do it in a different color. Rotation. Okay. I can now spend the next 45 minutes deriving these for you, or we can just cheat. Now, I'm not an advocate for cheating when it matters, but here it doesn't matter because I can spend time deriving it, or we can just flip all the symbols. What do I mean by that? We just learned that instead of, what's the symbol we use for velocity when something's in rotation? It's omega, isn't it? Right? So is it possible? Could it be this straightforward? That instead of v equals v naught plus at, it could be omega equals omega naught plus, and instead of an a, alpha, and t is t, there's no circular t, this is all t, okay? Could it be that we just need to switch symbols? No. Are those two first equations the same equation? Yeah. Yes, they are. I mean, I know they're written in different symbols. They're both screwdrivers. It's just one has a blue handle, one has a red handle. They're still screwdrivers, right? I mean, one might be Phillips, one might be straight bladed, but same tool. Don't go flying off the handle here. Oh, it's all new. Okay, how do we write the second one? Instead of a delta x, what's the thing for position now? What? Not the thumb, sorry. It's not r.
Theta?
It's theta, right? So instead of a position like x or y, we're going to do a delta theta. And instead of a v naught, we're going to put in omega naught times t plus 1/2 alpha. Good, you getting the idea? T squared. And instead of v squared, we're going to put in... Oh, good, right? K equals omega naught squared plus 2 alpha instead of an A, and instead of delta X, delta theta. And there we go. It's the same toolbox. It's the same 3 equations with a different code. Actually, what they've done is they've gone to a toga party. Right? They put their gigs on and parties happen. Okay, there are, a little bit of a caveat here. There are some relations that I'm going to give you here now, some equations, that are more like the Google Translate for going between the linear and rotational versions of this toolbox. Right? Just like in Google Translate, if you've got a website that's in Spanish and you need to know it in English or something like that, right? You can send it through Google Translate and it'll give you a really weird translation. Okay. Now, these are actually a better translation than Google Translate. Although, I've noticed something. Ever since ChatGPT, the translations seem to have gotten a lot better. Seems like they've upped the AI game when it comes to translating things. It's still a little bit wonky, and you can tell when somebody's translated it through ChatGPT, but we're getting there. We're getting there. Okay, what am I talking about? I already gave you one of the translation equations. This way of getting from what is really a linear thing. Arc length is a distance something traveled. I know it didn't travel in a line, but it has units of distance, right? And then units of theta or angle. Okay, so there's that one. But there is also a way to get from linear velocity to angular velocity and back again. And it's that angle right there. Why did I put a little t on that thing? This is the tangential velocity that something has as it goes around. Okay? So at any one point, if I freeze this in time, let's say this thing is rotating from your point of view, that would be counterclockwise, right? Okay. So as it rotates around like this, we can look at an instant in time, and at this instant in time, what direction is the ant going? That way, right? What direction is the ant going over here? right here. Down, what direction is the ant going at the bottom? To the right, okay? At every point along this motion, the ant has a velocity that's tangential to the angular velocity. That's what that little t means right there. The tangential velocity. Velocity tangent to the rotation. Okay? Works for a circle, doesn't work for anything else. And a similar one crops up for the, do you remember centripetal acceleration? Centripetal acceleration over here, right, was related to that tangential velocity squared divided by r. Well, we can write down, does the ant have centripetal acceleration? As the ant goes around on that bicycle, does it have an acceleration pointing towards the middle? Yeah, it's going in a circle, right? That's still true. We can write that as r omega squared. Basically, just put v sub t into that equation right there and you get r omega squared. But now there is a new acceleration that we've got to deal with, and that's the tangential acceleration. So in the red and green boxes here, you have what amounts to a toolkit with a couple extra screwdriver tips that you may need along the way for specific situations. But this tangential acceleration, tangent to the circle, right, that this thing is going around on, and if, for example, I've got the ant going along here, and I put my hand on here, and the alpha is negative, meaning it's the omega is slowing down, right? Okay. The acceleration that causes that slowdown of the circular motion, that creates alpha, is directed tangent, just like the velocity is tangent, but because it was slowing down, if the velocity is going around this way, what direction does the acceleration have to be? It's got to be down, right? And I can apply that acceleration anywhere. I can apply it up here, and it will be pointed backwards like that. But what if I speed up the wheel? Which way is the acceleration pointed compared to the velocity? Same or different direction? Same direction, right? So I can have positive alpha, negative alpha, but that corresponds to a positive or negative tangential acceleration. I know that might be kind of really the first new bit of information that is taking your brain and doing some violence to it. All right, so how do we use all of this stuff? I've developed the ideas, the concept, the toolbox, all that kind of stuff. How do we use it? Well, how did we use it before? What have I been on about for 8 weeks? What's the first step to solving any problem? You visualize, right? You try to get a picture. You try to understand what's going on. You get some information down on the page, right? Once you got, and we did lists. I showed you how to do lists right out of the gate, because I wanted you to learn the skill of identifying what different information, different numbers that they were telling you and the problems were, right? And then we went into some sort of strategy mode. And when it came to kinematics, that strategy was which equation do I use? Maybe one, maybe I got to use two, maybe only one, but which of these equations is going to help me solve for the thing I want? And then we did the math, and then we went back and we checked it, right? We've been doing that over and over and over again, right? Granted, it's different. It feels different when you're doing it for Newton's laws, and it feels different when you're doing it with energy, because the devil's in the details. But now we're coming back, right, to these methods that we've developed, okay? And we're gonna employ them again. And so we're gonna do this talking about hard drives. I chose this example not because all of you are gonna go out and become hard drive technicians or anything like that, but because one of the jobs I had in college was I worked for Seagate Technologies in their, what do they call it? Pre-sales technical support. So I was one of the people that was responsible for answering the phone and before a person had ever bought a hard drive, giving them technical support. On the surface, that sounds stupid, doesn't it? But actually, people would call us up, end users, but normally businesses, would call us up and say, you know, we need to build a server, and it needs to have this much storage in it, and it needs to perform this way. What kind of hard drive that you guys make do we need? And in what configuration and all that kind of stuff, right? So, long story short, I told people what to buy, essentially, okay? Based on what their technical requirements were. So one of the things that we use to measure performance of hard drives is something called spindle speed. The hard drive in your computer, now, computers nowadays are transitioning away from hard drives, at least our consumer devices are. Hard drives still very much in play in the cloud. But you might still have a computer that has a hard drive in it. You'll hear it spinning, right? If you ever turn the computer on and it does that, right? It's not the transmission in the computer shifting, it's your hard drive spinning up, okay? So a decently performing drive that you can just go down to Best Buy and buy would have a spindle speed of 7,200 RPM. What's an RPM? It's a revolution or rotation per minute, okay? So that's an interesting number. That has nothing to do with the actual units for what theta would be. What are the units of theta again? Radians. It's radians, okay? Not degrees. If you got it in degrees, you got to convert it into radians. More on that later, okay? So this hard drive spindle speed, the operating speed, the speed at which the platters are going around is 7,200 revolutions, complete circles, in 1 minute, right? And I also had access to the technical data that showed how much the electric motor in the drive accelerated those plates. And so 30 revolutions per second squared, again, is the acceleration that's being imparted as the drive speeds up. These two things would help inform how long it took a drive to get into a ready state. So not only do you have to spin the data platters up to a certain speed, but then the drive also has to go through an initialization routine that takes anywhere from 0.3 to 1.5 seconds, depending on the type of drive it is and all that kind of stuff. So we're going to figure out what that startup time is. Okay? From the time you turn the drive and give it power to the time it's ready in terms of it's spun up its platters to get there. And I've got a picture down here. Okay, these are the platters I'm talking about. The motor's down in there and it's spinning around. This is all a mechanism to move the read-write head around. But we're going to try and figure out what that is. Okay, so we can make a list. Let's go back to the list. The list is informed by the toolbox. Right? Just like it was before. So I'm going to, so first thing I could know or not know would be omega. Omega naught, alpha, t, delta, theta, and I think that's through the first, second, third, yeah, I think I've got all the things, right? That I could know or not know about how this hard drive is spinning up. Okay, do we know how fast the platter is going at the end of its time? What's the final speed of the platter? It's 7,200 RPMs. But 7,200 RPMs is not the standard unit for angular speed. Angular speed should have units of radians per second. So that means we need to convert this thing into radians per second. Do you want to do that now, or do you want to continue setting up the problem and we'll convert later? Convert later? Okay, let's just keep putting our information down. Do we know what the speed of the platter is when we turn the drive on? It's 0, it's at rest, right? Okay, that's good. Do we know the angular acceleration? Yeah, they gave me an angular acceleration. I'm going to call it positive 30 revolutions per second squared. And again, alpha should have units of radians per second squared. So revolution per second squared is not a standard unit. So we got to convert that. Okay, do we know how, and why positive? Why am I saying the acceleration is positive? Is it speeding up or slowing down? Speeding up. Okay. Time. Do I know how long it takes? Nope, but what are they asking me to find? They're asking me to find that time, right? We're going to circle that one. Do we know how much it like rotates around as it starts up? We're given anything about how far the platter travels in radians? No, they're not giving me that. Okay, so all right. Do you want to continue the problem-solving process or pause for some conversions? Conversions? Just get those out of the way before we do anything else. Okay. How do I convert revolutions per minute into a radian per second? Well, let's rewrite. So it's 7,200 revolutions divided by minutes. That's what the per means, right? Revolutions per minute means divide by minutes. Okay. Let's tackle, which one first? Minutes or revolutions? There was two choices. We'll do revolutions first. Okay. In one revolution, one complete circular motion, I want to get to radians, don't I? Do I know anything about how many radians it takes to go around once? How far is that in radians? 2 pi, right? You go around a circle once, you've done 2 pi radians. For every one revolution of a circle, there are 2 pi radians. Okay, so we've managed to wipe out the revolutions. That's good. I got radians per minute now. So now I got to tackle the minutes. For every 1 minute, how many seconds are there? 60, we know that. Okay, so let's see here. The minutes have now canceled. And so basically I need to take 7,200 and multiply it by 2 pi, divide by 60 in my calculator to get 754 radians per second. And now I'm in my standard unit. I'm going to be safe. You can work in like revolutions per minute, and we could convert the revolutions per second squared to revolutions. I wouldn't do any of that. You might see that on YouTube if you're watching other stuff. Just realize that the standard unit is radians per second squared. You get to those, you'll be safe. Okay? It actually turns out to be a little bit less work to just go to the safe thing than it is to try something fancy. Okay, while we're here, just real quickly, how do you go from degrees to radians beyond asking your calculator to do it? How many in 2 pi radians? In 2 pi radians, how many degrees is that? 360 degrees. The reason you keep saying 180 is that you can divide both sides by 2, right? Okay, and there's pi radians equals 180 degrees, right? So halfway around the circle is 180. So there's your conversion factor for going back and forth between degrees and radians. So if you're ever given degrees, you can get to radians. Okay. Do note, this is a point of confusion that will come up later. The radians mode on your calculator, degrees, radians, all that crazy stuff, only matters if you're doing sine, cosine, and tangent. Okay? We'll get to that later. I'm just saying, you don't need to put your calculator into radians mode to do this math. This is all straightforward math. Keep it in degrees mode, even though we're working in units of radians. Okay. Revolutions per second squared. So do we need to worry about the second squared? Nope, second squared is good, right? That's our standard unit for time. So we got to convert the revolution, don't we? Now we know how to do that. For every 1 revolution, there's 2 pi radians. And so that's 60 pi or 188.5 radians per second squared. Okay, so there we go. We took a little bit of a necessary tangent to get our units all sorted out. Okay, now I've got to figure out what the heck, what am I doing? What am I solving for? Time, how do I know? Oh, Pass Me circled it. Thank you, Pass Me. Okay, so we're solving for time. We know omega, omega naught, and alpha. Turn to your neighbor and tell them which of the kinematic equations is best to use. Go. Which one? The first one. Use omega equals omega naught plus alpha t and solve for t. Again, using my best practices of leaving notes for my future self when I come back to look at this and go, what the heck? What did I do? Oh yeah, I used the first equation and solved it for t. Okay, so solving this for t, move the omega naught to the other side, becomes negative. Divide both sides by alpha to get my t. So t is going to be omega minus omega naught over alpha. Now I can throw in some numbers. 754 minus 0 all over 188.5. Since I've put standard units of radians per second squared into this, I know I'm going to get the correct units for time. So all I got to do is throw the number in. And I get a time of 4 seconds. So the startup time for this hard drive, 4 seconds. Or at least to get the platters up to speed. There's an additional time to get, like I said, for a little bit of calibration that the read-write bit has to do. All right. So now we found that time. It would be really nice to be able to go back and check this, but I mean, we could maybe try to solve for the delta theta and go back through that way. Seems like a lot of extra work, and this seems reasonable, so I'm just going to go with it, see what happens. But the second question is a little bit more interesting, okay? So on a hard drive platter, there are sections, I did that in the wrong spot, didn't I? There's sections on this platter. My circles just aren't working. Here we go. Okay, where data can be written. Okay, and it looks a little bit like a donut in a sense. On this picture right here, I don't know if you can see it on the screen. Like there's only so close that you can go to the center of the drive and still be able to write data effectively. And then the same is true for the outer edge. It's only between these two distances that the data exists. There might be more platter there, it's just data is not written there because it gets really hard for the read-write head to be over those locations consistently. So this second part of the problem is asking us to figure out how fast the platter is rotating underneath that read-write head that floats along the top here, okay? So this drive platter is spinning around. There's this thing that sticks out and just floats really close to the surface of the hard drive. As a matter of fact, if you've ever heard of a hard drive crashing, that used to be a literal thing that happened. The drive head, the read-write head, would get into, maybe it got dropped or vibrated too violently, and the head would literally hit the surface of the drive as it was spinning, and either destroy the head, destroy the data that was on, like physically destroy the data. Nowadays, when hard drives crash, it's more of a logical error, meaning software's gone bad, calibration's gone bad. You actually have a problem, unless you've dropped the hard drive or like shot it with something, it probably isn't a physical problem with the drive. It's a typically logical problem, which means that data can be saved. And I spent a long time in my college career after this job, saving people's term papers and stuff like that. Just don't keep all of your term papers on a USB thumb drive or a floppy disk. Have it backed up in at least 3 places. Okay. And you're like, what do you mean back up, Mr. Balogh? All my stuff's in the cloud. That's a different class. Don't get me started. Not that the cloud's bad. It's good. It's just not what you think it is. Anyway, okay. So, where was I? Oh, speed underneath certain points. So there's like an inner radius and an outer radius. They want to know how fast. If you were ever just asked, how fast is something rotating? They're probably talking about velocity, like in meters per second, not radians per second. Like they'll ask, what's the angular velocity? Now they're wanting you to answer in terms of omegas, right? So to get part B here, right? What we're going to do is we're going to take and we're going to figure out that Google Translate equation that gets us between omega and V. We know that the omega for the inner and outer is the same, right? Doesn't matter where you are on that circle. On this bicycle wheel, right? If the ant's in here or it's out here, does it go through exactly the same angle in the same amount of time? Yeah. Okay. But the ant's moving faster tangentially the further it is from the center of the bicycle wheel. So this tangential velocity that they're asking us for is going to be how far we are from the center times how fast we're going in an angular sense. Well, for the inner radius, please tell me I have this written. Yeah, there it is. Okay. What do I put in for the distance? It says 1.5 centimeters. What do I do with that number? You convert it, right, to meters. 0.015. It's just a lot of noisy chemists out there. Just giving me the finger. All right. Omega? Do we know what the final omega is? Yeah. What is it? What number do I put in? Good. 754. You guys are awesome. Okay. We multiply together and we get 11.31 meters per second, which is the answer, which is about 25 miles an hour. Okay. And then to do the other one, instead of 0.015, it's now 4 centimeters. So 0.04, and then 754, again, same omega. And that one is moving at 30.2 meters per second, which is the answer, which is about 68 miles an hour. These hard drive platters are really moving inside of these hard drives. And that's just for a 7200 RPM drive. You can buy 10,000 RPM drives. It's moving even faster. You get 15,000 RPM drives, and I think there's a manufacturer that does a 24,000 RPM drive. The thing is the faster these hard drive platter spins, yes, the performance is better. You can read and write data much faster. But the amount of errors you get and the amount of time you're spending correcting those read-write errors starts adding up and giving you diminishing returns. Plus, the hard drives don't last as long when they're spinning faster, which is why a lot of data center drives will have 5,400 RPM spindle speeds or even 3,200 RPM spindle speed. They'll spin them slower, but you can rely on that drive a lot longer than you would if you were spinning it faster. There was, Seagate did work on a drive, Seagate, IBM, one of the two, where they were trying to spin it at like 40,000 to 60,000 RPM. And what would happen is the platters would destroy themselves. They'd literally just fly apart in shards. And these platters are made of a glass metal alloy. And so you get these shards flying all over the place inside the drive. And you'd open up the drive casing and there would just be a pile of glass in there. And they couldn't figure out what was going on because in terms of the material, it should be able to hold together no problem. Well, what they discovered is that for certain size platter, at about 45,000 RPM, the outer edge of the platter was going so fast that it was breaking the speed of sound before the inner edge even got close. You see how there's like 25 miles an hour and then 60 whatever miles an hour, right? So there's a difference there. What they were doing is they were breaking the sound barrier on the outer edge without breaking the sound barrier on the inner edge. The outer edge, as it broke the sound barrier, it makes a sonic boom and start the outer edge flopping up and down while the inner edge was going, what's going on, right? And the drive would literally blow itself apart as this vibration set up. You can go on YouTube and see, people do it now with CD-ROMs, right? I think the slow-mo guys have a video where they're doing laser discs and they just spin them so fast that they just throw themselves apart. There, it's a plastic failure. It's not they're hitting the speed of sound or anything, but it's still a pretty cool video. Anyway, that was a real trip down nerd memory lane. Jeez. But I hope it shows you that doing these kinematics problem, did it feel familiar at all? Tiny bit, maybe a little bit of a memory back there. Consciously, you could be going, I don't quite remember. Your brain is going to remember. It does. Subconsciously, it's seen this before. And those connections are going to be made smoother now. Okay? They're just going to go faster. It's going to be great. Yeah, we got time. Let's do a quiz. We got time for one.